Again, welcome to our lectures on linked list. So we're going to have two parts in a linked list. This will be a linked list part 1. Again, this is the introduction to data structure class. And what I will mention by linked list is that we can use it to implement both stack and queue. We already talked about stack and queue using array implementation. Now, the difference between array implementation of stack and queue and a linked list is that in array, we have a face size. So when I create an array, I have to specify the size of the array. So the array can be, again, full or it can be empty. With a linked list, we dynamically allocate the memory space. What we mean by dynamically is that during the running time of the program, we are going to allocate a memory space to our objects that we create with a linked list, as that stack or queue. So this means that in linked list, there's always a space that was stack or queue will never get full. It will never get full. It will only get full when the memory of our computer, I mean the hardware, the memory is no space or is full. So linked list again never get full. So let's go through the lectures. First, we are going to discuss about what is a linked list, what are the operations of a linked list, and how we can implement it. Then later, we will talk about, in a different lecture slide, we're going to talk about both the stack and queue implementation of linked lists. So our main objective in this lecture is to learn about linked lists. We're going to study the basic properties of linked lists, also explore how we can insert and also delete items from a linked list. And we're going to also discuss what is a linked list, what consists of linked list, how to build it, and how to manipulate it. Normally, manipulation of a linked list is how do we go through the linked list? How can we remove an item? How can we set a new item, etc.? Also sorting, etc. So here, what is a linked list? Here we see a linked list is a data structure used for collecting a sequence of objects. So a linked list is, again, it's a very simple data structure used for collecting a sequence of objects. And a linked list consists of what we call the node. The node. Each node have two items: the information that we want to store, and also the address of the next node. Sometimes also we may have what we call the double linked list, which means it may have information that we store, the address of the previous node, and the address of the next node. Here we are talking about a very simple linked list. So two parts, the address of the next node and the data. Example, here we say each node in a linked list is connected to the neighboring nodes. So the neighboring nodes that is connected to must have the address. So it's more or less like a pointer in a C language. If one node is pointing to the other node, they have to have the address of that node that is pointing to. When I said address, I mean the memory space, the memory address. So a node is an object that stores an element and the references to the neighboring nodes. References means the address. So this is there's this concept for us to understand. So here, for example, we have a linked list and we have 3 nodes. So we have a node Tom, Diana, and Ari. Again, this is just a simple example, but normally we're going to have 2 parts in the node. Where the Tom goes, that is the data. Then the address of the next node. And here we can see that we have a double arrow. So which means we have 3 parts: the address of the previous node and the address of the next node. Then what makes linked list very special is that we can add and remove an item in any way of the linked list. It can be in the beginning, the end, in the middle. It's okay. And we can also visit the elements of the linked list in sequential order, more efficient. So to insert an element or a node into a linked list, all we need is the pointer. So here we can see that previously Diana points to array. Now we are going to change, we want to insert a new node. First step, we have to create the node, because since this is dynamic allocation of the memory space, anytime we have a new item, we have to create a node. So we create a node, then we assign the information to the node, then we change the pointer. So instead of the Diana to point to array, this time it's going to point to Romeo, and Romeo will point to array, which means I'm inserting a new node between Diana and array. Now, if I'm removing an item from the linked list, the second diagram, we don't need to create any node, because here we want to actually to destroy one node, remove it. So we also need to change the pointer. So instead of Tom to point to Diana, we're going to assign the pointer to Harry. Then we are going to free the Diana memory location. So here we say when inserting or removing a node, only the neighboring node references need to be updated. The references again is the address. So instead of Diana pointing to Harry, we're going to say Diana will point to Romeo, then Romeo will point to Harry. That's to insert. Now to remove, visiting the element of linked list is sequential order, and that's more efficient. Random access is not efficient. So random access rather is good for array implementation. So array, if I want to move to any item, all I need is the index of that item. So when to use the linked list, if we are more concerned about the effectiveness or the efficiency of removing and inserting an element anywhere, then anywhere in the list, then linked list is a very good way. And here we say we rarely need element access in random order. If it's random order, then I would say array is more better, because array we just have to refer to the index. And one thing we mentioned here is that Java program, the Java library file or package, has a special class called linked list. So a linked list is more or less like a Java collection framework or Java application, Java program interface, etc. Now, if I want to use the linked list class in Java library file, I'll have to import a utility package. So java.util. The utility package also consists of stack class and also the queue class using array implementation. So linked list class in the Java API has methods of collection interface. And these are some of the examples. So here we can see we are creating a new object, the linked list object called list. So we use the class linked list. The data type is string. Then we use the keyword new to dynamically allocate the memory space during the running time. And of course, the constructor linked list. So the first option here, create our list object with nothing inside. So we can see the constructor is open, empty parentheses, empty argument. Now we have a method called add last in the linked list class. Now when I call the method add last, it will insert an item at the rear of the linked list. And as we know, this is object-oriented programming. We have to start with the object name first. So list.addLast, we are adding array. Then list.add first, we are adding solid in front of the linked list. So add last, add from the rear, add first, add in the front. Then we also have a list.getFirst. So the getFirst method is to tell us what is in the node in front of the linked list. We are not going to remove it. Just want to see. Same thing applies to get last also. So list again is the linked list object dot get last. This will show us the last item. Then we also have the remove first. So removes the first element of the list and it's also going to return it. So if I have remove first Sally, then we are going to remove it. But get first means I want to know if Sally is in the front. But remove first, if Sally is in the front, then we're going to remove it. So these are some of the applications and the methods in a linked list class Java API. So let's see some example here. Here the question saying, do linked lists take more storage space than arrays of the same size? The answer is yes. And the reason why linked lists take more storage space is that every node we create, we must have the address. In array implementation, we don't need to know the address of the element. All we need to know again is the index, and we access the items. Now, why don't we need iterators with array? We don't need iterators with array because in array, we can access any of the elements in array using their index number. So we don't need it. Iterators is a special object that we use to go through an item in a list, or when I have more than one item in an array or something. But we don't use it in array. So here we say we can simply access each element in array with the index number. Now the question is that we should write a loop that removes all strings with length less than 4 from a linked list of a string called words. Now there's a trick here. As we said earlier, in array, if I want to go through an item in array, all I need to do is to refer to the index of the array. But with linked lists, we have to use iterators. We can use iterators to go through an element in array. Iterators locally is a Java API. So we don't need to write the code. And this API has at least 3 important methods. The first method is as next. Since I'm going through an element in a linked list, as next method, I will use it to check if there's another item in the linked list or we have reached the end of it. So as next always will be like a condition to check if we still have element to go through in the linked list. Then we have a method also called next. And next means to move one step forward. We have items in the linked list. I mean, number 1. If I say Intel, the Intel now is the iterator object. So you can look here, we create list iterator, the type is string, and we create the object Intel. So Intel is an object, and here we are saying Intel.next, which means we want to move to the next item in the object. So now let's go through the code. Oh, one more method. So we also have a remove. So we have as next, next, and remove. And remove means to remove an item from the linked list. So let's go through the code. You can see the first thing we do, we create our iterator using the iterator constructor. And our iterator name is Intel. So anytime I want to go through the linked list, I'm going to refer to Intel since we use iterator to go through item in the linked list. So here I said while Intel dot as next. As we said earlier, as next, check if there's a next item or we have reached the end of the linked list. And we are using the iterator object to move through the linked list. So here we say while the Intel dot as next. So if this is true, then we move to the next element. So Intel dot next, we assign it to a data type, string variable name str. Now we check, okay, so if str.length is less than 4, then we are going to move the item. Now we still have to refer to the iterator object inter, so inter.remove. So that is the code, because this code says we should write a loop that remove all strings with a length less than 4. So that's my condition here now. If the string that we access, the next string that we access, the length is less than 4, then we remove it. So we call inter.remove. And that's what's the question here. So first thing we do again, we create the iterator object called the inter. Then we use the while loop to check if we have item in the linked list. If we have an item, then we move to the next item. We check if the length is less than 4. If it's less than 4, then we remove it. Another question, they say we should write a loop that print every second element of the linked list of a string called was. So this also we have to use the iterator. So here we create our iterator object named intel again. We check if we still have an item in the linked list. Well, if we have an item in the linked list, then let's print it. But we print and skip one item. So we say inter.next to move one step forward before we print it. Now we say if inter.asNext, then we move to the next item. So that's the concept of a linked list. Now let's go through more detailed lectures there. So a linked list is a list of items called nodes, as we said earlier. The order of the nodes is determined by the address or the link stored in each node. Every node except the last node always contains the address of the next node. Even the first node point to the first node in the linked list still have the address of the first node. The component of a node is two things. We have the data where we store our information. Then we have a link part that we store the address of the next node. This is very important again because of security issues. So this is a linked list. The structure of a node means we have two parts, the info and the link. And here we have a linked list with 4 items. So we can see some textbooks use the term head. We use the term head. Head or first is the special node that point to the first node of the linked list. So it's called head or first. Then we can see the next node point to the previous, to the end. The last node in the linked list always point to null. So we say the head or first. That's the first node in the linked list. It always holds the address of the first node in the linked list. And we said the info part of a node can be either a value of a primitive type or it can be of a reference to an object. So here what we mean is that a linked list, we can store both primitive type data or we can store, again, a reference to an object data. So since we said a linked list consists of node and also node consists of 2 items, which is the info section and the address section. In the linked list, we're always going to use the class called node. So class node will be inside the linked list class. Because anytime we want to create a new node, we have to call the class node. So this is an example of a class node. Again, the keyword public class. The name of the class is node. Node have 2 instance variables, as we said, the info. Here we are using int as a data type, but the data type can be any data type. Then we also have the address. So this will be the link, the address of the next node. We should consider the following linked list. With 4 nodes, we can see the position of each node with the info link. So now we're going to see some example. First, we say, what is the head? The head is 2000, as we can see. The head is 2000. Now, what is the head.info? Here they say 17, which makes sense because head info 17. Now, if I have a head info, head info, that will be 63. So we have head info, then head link info. Let's see head link info. So head link info means I'm in here, head, the link is here, and the info, so it will be 92. So that's the concept here, going through the item in the link list, head info, head link dot info. Now, when I have a link list and I'm using the head to go through the item, what happens is that my previous node will be cut off from the link list, which I don't want that. So for example, if I move the head to 92, if head is pointing 92, most likely the first node will be removed. So that is the concept. So because of that, we always create a new pointer, and we want the pointer to start at the same place where the head is. So this is our new pointer, is called current. So you can see here we assign head to current, which means current also will be 2000, as we can see here. Then now I can move it along and we still keep our link list because again, the head is still there. So here we have a current.info, which means we move one step to the info, then current.link, which means we move to the link. Let's go back and see what we're trying to say. So current.link means I'm here current. The link is 2800. Current.link.link.data will be 63. So that is the concept here also. Now we can see that we move the header to this position. And normally to do this, we can say current.link equal to current. So current.link assigned to current is the same as saying current plus the next item assigned to, so I'll say current plus 1 assigned to current, moving one step at a time. So here we have current is 2800. We can see the position. Then current.info will be 92. Current.info will be 45. And these are some of the examples. Again, you can go through this example using the previous slide. Now let's start to build our linked list now. But before that, we're going to see the algorithm that we can use to transverse a linked list. That's to go through a linked list. So the basic operation of a linked list requires us at least to search an item in a linked list. We can insert an item or delete an item also. So the basic operation for linked list is again search the list for an item, insert an item in the list, or delete an item from the list. We cannot use the head, as I said earlier. If you use the head, the previous node will be gone, will not be part of the, again, the linked list. So we always here, we say we assign current, but we can assign any variable, again, to the head. This time we call it current, so we say current assigned to head. So first of all, we have this. This means I can now use the current to transverse through the list. The head will stay so that the linked list stay. So here we say why the current not equal to null, then current equal to current.link. So which means when we haven't reached the end of the linked list, because the last node in the linked list always point to null. If we haven't reached the end of the linked list, then move the counter one step. So current.link equal to current. The following code also output the data stored in a node. So the same thing, since we're going to transverse through, we assign the head to the current. And we say that if the current is not equal to null, then we should print out the info. So here we are printing current.info. After that, we move to the next node. So current equal to current.link. So we can also insert an item and delete an item. But before we insert an item, we need a class node. So this is a class node. The node have two parts, the info and also the link. So here we want to create a new node with info 50 and insert it after P. So first we have to assign the new node to 50. Then the next step we have to assign to the link. So the following statement, we insert the node in the linked list at the required place. So we say that we assign P link to new node link. Then we assign the new node to P link. Again, this is how we insert a new node. Then the sequence of statements to set the node is very important. So if I said new node.pin link and then pin link to new node.link, what will happen is that it's going to create our node opposite way because of the pointer. Now the sequence of statements to insert the node is very important also. So this is the example we are saying. List after the statement p.link assigned to new node.link. So inserting, again, we use two references variable. You can simplify the code somehow. So instead of, again, inserting an item with only one pointer, if I have P and Q, it's very easy because here I'm going to set both P and Q into the new node. P will be in the front, Q will be in the rear. So the following statement is set a new node between P and Q. So we can see we assign, P comes before Q. So we assign Q to the new node link. Then we assign the new node to the P.link. Or we can say the new node assigned to P.link, the address. Then we can also say new node.link assigned to Q. The order in which this execution happens, in this case, it's not really important. Again, we have the data online, everything. So this is an example here. We can see we set the 65 instead of pointing 35 for it point at 50, and the 50 also point at 34. So this is again new node assigned to P-link. Now next we assign the Q to new node.link. So we can see the Q be assigned to the new node.link 34. So to delete an item, we just move the pointer to free. So node to be deleted is info 34. And I want to delete the node with the info 34. So what I'll do is moving the pointer. So the following statement, remove the nodes from the list. P.link.link assigned to P.link. And this will help us again to remove the item after we deleted it. So previous statement removed the node. However, the memory may still be occupied by this node. So systems automatic garbage collector, which we know Java is have a built-in garbage, will recreate the memory occupied by unreferenced nodes. And this is deletion. You can see we assigned, again, we are using the P and Q, 0.2 pointers. So we assign the p.link to q, then we assign q.link to p.link. The goal here is to move the q. Then here we make sure that we assign node to the q. So that's the diagram showing the deletion. We assign p.link to q to execute, then q.link to p.link, and that will remove the item 34. Now, how do we build a linked list? There are two ways. We can either build it forward or backward. Forward means a new node is always inserted at the end of the linked list. And backward means a new node will always inserted at the beginning of the linked list. So we need 3 references variables to build a linked list. One variable will point to the front of the list, which means we cannot remove it. And one will point to the last node of the list, and one will create a new node. The next 2 slides will show us how to do this. So this is build list forward. So we said we need the first node. We need to create a node. Again, building means I'm inserting a new item. So here we use the variable new node. This is the variable we are going to store the built-in again when we get a new node. Then this will show us the last item. Then we have int num also. So here we have system.out.println. We should enter the integers ending with our sentinel value will be -999. We ask the user to enter the integer value. So we use the console.nestInt. We assign node to the first. And here we say while num not equal to the -999, the sentinel value. What we do, we create a new node. We assign the number to the new node, and we assign the address to the again. So here we can see again a node. It's create a new node using the constructor, default constructor. Then we assign num to the node have 2 parts, the info and the address. So we assign the num to the info part, then the link point to null. Again, why? Because that term is spin. So new assigned to new node.link. Now, this is our most important condition. We say if the first equal to null, this means there's no any item in the linked list. So if there's no any item in the linked list, then the first node that we insert will be the first and last. So we assign new node to first and new node to last because there's no item in the linked list. If first equal to null. If there's no item in the linked list, then we assign our first node will be both the first pointer and also the last. Else, our new node, we assign it to the last.link. Remember, we are building forward. So we have to assign the item in front forward. So that's why we assign new node to the last link. Then we assign new node to last. After that, we ask the user to enter the new integer value. So again, this is a very straightforward way of building linked list for us. So I start from beginning again. We need at least a minimum of 4 variables, the first and the last to keep track of the first and last. And then creating the new node, we have a variable new node to put in, then the num information. So we ask the user to enter the integer with the sentinel value to stop it. When user enter it, we check if it's equal to the sentinel value. If it's not, then we dynamically create a new node. So we say new node using the constructor. Then we set the info part of the new node to num, then the link part to null. Then we check if there's an item in the linked list. So first equal to null. If it's true, then the first node we set, the new node will assign to first and also will assign to last. If it's false and we have an item, then we jump to the else statement, which is this section. Then we assign the new node to the last.link, the new node to the last. We can also build a linked list backward. Backward means we're going to set at the first section instead of at the end. So the backward, we need the first new node and then the none. We don't need the last because we are setting the item at the last in the beginning, the backward. So we ask the user to enter the integer with a sentinel value, same thing as previous. We check if first equal to null. If it's equal to null, then while we haven't entered the sentinel value, we create a new node. We assign the value to the new node info, and we assign the address to the new node.link. This is creating a new node, assigning the value, address, then assign the new node to first. Then later we ask the user to enter an integer. So this is the linked list ADT. You can see all the operations that it performs. The cron is empty, initialize, print, length, front. Front is to see what is in the front of linked list. Back is to see what is in the back of the linked list. Then the length print. You can also search an item or insert first or insert last or delete the node. So there are two ways of linked list. We have the sorted and we also have unsorted. We will discuss about this when we go through the code in the classroom. So the algorithm to implement some of the operation differ for sorted and unsorted lists. So therefore, define the linked list class as an abstract class. And the linked list class has two derived classes, the unordered and then the ordered linked list. The structure of a linked list node, as we said earlier, again, each node consists of two parts, the info section and the address of the next node. So each node of a linked list must keep track of the data as well as next node in the list. The node must have at least two instance variables, the address and the content. And then we can define the linked list node as inner class of a linked list class. Again, we will go through this code in the classroom. So this is the structure of a linked list node. And this is our instant variables, first and last, and then count. We say the linked list iterators use at least three methods. The next, has next, and also next. So this is our main class now. So here we have the instant variable linked list node. We are using the template, and then the last template count is int. And the same methods we had previously. So but we include the constructor. So we have a default constructor here. We can also have the full constructor here also. So this is our first method to check if it's empty list. So it's empty means we return if first equal to null. Default constructor, we set the first and the last to null and the counter 0, which means there's nothing in the linked list. Initialize list, we make sure there's nothing inside, so we set the first and last to null and the counter. So it's the same as default constructor also. And we can print an item in the list. Using the y current not equal to null, we can see that we are using a second pointer to go through the items in the list. While we are going through each, we will print it using the system.out.print. And the length of a list, we return the count, which will be a special variable in our instance variable. Anytime we insert an item, we increment the count. Anytime we remove an item, we decrement the count. So we're going to end somewhere here, and I will continue the part 2 from here again. Again, thank you and wish everybody the best.